Hey all, here's a brief introduction to lung disease, building on what we talked about at the Open Door mission earlier this week. So, first we'll review some of what was discussed while there. These are the lung volumes and capacities. When you're looking at these, a volume is a single quantity, and a capacity is the sum of at least two, sometimes more volumes. So you'll have to learn this whole chart for pulmonology. We'll just go through it quickly right now. When you're sitting breathing quietly, that's tidal breathing. And so this is called your tidal volume. You go in, you go out. You can all take a tidal breath. You're all taking tidal breaths as you watch this. If you breathe in as much air as you possibly can, that is your inspiratory reserve volume, is from the top of tidal to your maximum total air. If you blow all the air out that you possibly can, that is your expiratory reserve volume, from the bottom of tidal to the bottom of the maximum possible expiration that you can do. And then there's always some air left over in your lungs at all times. That's called your residual volume. Your lungs have a very high surface tension in the alveoli, and without a little bit of air staying in them, they would collapse. We don't want that, so you have residual volume. And those are the four volumes. And you can add them together. So there's inspiratory capacity, which is tidal volume plus inspiration. There's functional residual capacity, which is expiratory reserve volume plus residual volume, and is what it sort of sounds like, how much air is left over at the end of a normal breath. And then there is vital capacity, vital related to breathing, related to life, the total of all of the air that you can actually move. So it's inspiratory reserve, expiratory reserve, and tidal volume collectively is your vital capacity. And all four all together is the total lung capacity. The other volume that you'll need to be aware of as we progress forward is the forced expiratory volume, and that is how much air that can be forcibly expired after maximal inspiration. You can mark this in any way you want. So there's FEV1, which is forced expiratory volume in 1 second. There's FEV3, there's FEV5, but the one is the one that you need to be aware of. How much air can you get out from maximum inspiration in 1 second? And these are the sorts of things that we look at in pulmonary function testing. So here again is those, or are those volumes rather. So once again, here are the capacities. And as you look through a breath, we saw Grace doing this on Monday at the Open Door mission. What is graphed here is just the expiratory portion. So inspiration is going to be down here. Oops, I'm sorry. Inspiration is going to be down here, but this is not drawn because we're trying to relate all of this together. So these curves are called flow volume loops, named for the two axes. Volume is on the x-axis, flow in liters per second is on the y-axis. And the reason that these are helpful is because they make these characteristic shapes based upon your lung architecture. One thing that is confusing about them is that most of the time, but not always, the volume in the lungs is on the x-axis backwards from how you think it should be. 0 is somewhere over here, and the numbers go up as you move to the left. Why do they do it that way? I'm not actually sure. It's confusing, but that is how it is done. And that means that the far right, the lowest volume, because remember 0 is over here and like 8 or 9 is over here on most graphs, so always check the labels. The lowest volume at any point along the curve is the residual volume, how much air is left in the lungs when it's all been blown out. And the highest volume at any point, so where it crosses the x-axis on the left side of the graph, is the total lung capacity. How much air is in the lungs total when you're at the peak of inspiration. And then the forced expiratory volume is on here. So another thing that's confusing about this graph is that there is no time axis. So you can't actually say just from the shape of the graph how high the FEV1 is, because you don't know where the FEV1 cuts off. This graph is marking it for you, and typically the flow from maximum inspiration, so you could see when Grace did this, she breathes in and she starts to blow air out, and the flow increases dramatically to a peak. It peaks very quickly within the first second, and then starts to drop again because you're not able to force air out as quickly once you don't have as much air in the lungs. Somewhere along this curve on the downslope, you get to the end of FEV1. So the forced expiratory volume is the difference between total lung capacity and wherever the lung volume is at 1 second. And then the forced vital capacity is just the vital capacity. And the vital capacity can be expressed as the inspiratory reserve plus the tidal volume plus the expiratory reserve. Or it can be expressed, since it's all three of these things, as the total minus the residual volume, which is the way that it's probably easier to think about it on this graph. So the total minus the residual volume. And this you can get just from looking at the chart. Other numbers that we sometimes think about are peak expiratory flow, which is the highest flow that you achieve, usually very early in expiration. And then these FEFs are how much air, it's how much flow you have obtained at 1/4 of the way from your total lung capacity to the RV. So 1/4 of the way through your vital capacity, halfway through, 3/4 of the way through. The difference between FEF 75 and FEF 25 can be a thing, or possibly FEF 25-75 is the average of the two. I don't really remember. I'm not a pulmonologist. You can tell how often FEF 25-75 comes up in the things that you're about to do, which is not very often. Okay, so with all of that, then, there are characteristic changes that happen in different kinds of lung diseases. And so a normal loop is like we just described. It's high peaking, and it's got this nice shape to it. And the two major types of lung diseases are obstructive diseases and restrictive diseases. And like we talked about at ODM, I want you to think about obstructive diseases as problems with expiration. For whatever reason, something is blocking the flow of air out of the lungs. The classic example of this is COPD. And in that case, it's structural damage to the lung makes the airways floppy. And when you try to blow air out, the lungs collapse on themselves. And you can't blow air out because they're blocked. And so the expiratory portion of the curve is lower because the peak flow is not nearly as robust as in someone with healthy lungs. And the curve has this sort of scallop shape to it because you will just be blowing out and blowing out and blowing out and blowing out. It takes a lot longer to get out as much air. And so you'll see this. This is a subtle physical exam finding that can clue you into someone having an obstructive lung disease. It is, in a normal, healthy person with healthy lungs, your inspiratory to expiratory time ratio should be about 1:1, maybe 1:2. So it's breathe in, say for 4, and breathe out for 4. In and out. And in someone with COPD, it's more like this. Breathe in, and then those ratios can get up to 1:4, 1:8, 1:16 if it's really, really, really bad, I think is possible. And so you can see that the curve has this wide scallop shape to it. Another quirk of obstructive lung diseases is that the total lung capacity tends to be higher. The airways get hyperinflated, and the residual volume tends to be higher. So you can see that the residual volume on the green chart might be somewhere here around 2 or 1 maybe liter. But for this obstructive lung person, it's over 2 liters. And the reason for that is air trapping. When you can't get all of the air out in a given breath, the air is going to stay there. And over time, the lung will get fuller and fuller and fuller. And there is a perceived breathlessness for these people. They can't get enough air in. But the reality is they have a lot of air in there. It's just mostly carbon dioxide. It's not oxygen-rich fresh air because they do not move air in and out very well. This also means that the total lung capacity is much higher. So this person's is 8 liters as opposed to the 6 that you might expect in a healthy person. And this is visible on chest x-rays. This is a great clue that someone has COPD, is that when you look at their chest x-ray, the lungs will look gigantic. And the diaphragm will actually look flattened, and you'll see both of those things when you get to pulmonology. Or if you want to look up COPD chest x-ray, you can do that now. On the other hand, restrictive diseases, there's some kind of problem with, as we talked about, inspiration. For whatever reason, something is preventing air from moving into your lungs. So some examples of this are obesity. The chest cavity gets tighter in people with obesity, and so they have a sort of restrictive lung disease. The archetypal example is idiopathic pulmonary fibrosis, where your lungs just turn into scar tissue. And you can't move air through scar tissue. So the volumes all tend to decrease. Other things can do this, like if you have ankylosing spondylitis or neuromuscular diseases and your muscles aren't strong enough for you to breathe, that also has a restrictive physiology. There are a couple of different things that can happen. So the first thing that you need to notice about this as far as the loops are concerned is that the volumes are all shifted lower. Remember, 0 is on the right side of the graph in these charts. So the volume is shifted lower, the residual volume is very small, and the total lung capacity is also drastically reduced, depending upon the severity of the disease. The peak expiratory flow is once again diminished, but the inspiratory to expiratory time ratio is probably going to be the same. And so the most fundamental finding is that in obstructive disease, FEV1 to FVC ratio, if you divide FEV1 by FVC, that number will be much less than 1. In COPD, it has to be less than 0.7. Whereas in a restrictive physiology, that ratio is not changed really in any significant way. It can be normal, it can be slightly elevated, but it will not be less than 0.7 because the inspiratory to expiratory time and the ability to get air out quickly is not in any way affected. It's the overall volume that is diminished. So the shape of the curve, as you can see now in its fullness, is relatively similar in restrictive and normal, as opposed to this very different shape in obstructive, but the size of the curve is much smaller in restrictive. You're not able to move as much air. So to recap all of that, obstructive versus restrictive lung diseases. Obstructive is a problem with expiration. The archetypal example is COPD. The FEV1 over FVC is decreased. In COPD, it's less than 0.7. The total lung capacity is increased because of air trapping, and you treat it with bronchodilators, which can help open those airways, remove the dead air, and move air in and out appropriately. Meanwhile, in a restrictive physiology, the problem is more with inspiration. The classic example is idiopathic pulmonary fibrosis, although there are a lot of things that can cause it, including obesity. The FEV1 over FVC is normal-ish. It can be a little low, it can be a little high, but it will not be less than 0.7 unless there's a mixed picture, which we don't have to get into. The total lung capacity is decreased, and that's the fundamental problem. And these are very difficult to treat. You want to treat the underlying cause, but sometimes that's not possible. If someone has ALS, you can't really help them, at least as far as treating the underlying cause. If someone has idiopathic pulmonary fibrosis, there's not a whole lot you can do. If someone has obesity, then this is something that can be improved over time, but you want to treat the underlying cause. So text or email me if you have any questions. I hope this was helpful, and I hope everything is going really well for you.